Okay, so before I go into technicalities, I want to say a few more things which are just for general culture, conceptual clarity. So I refer to this picture from the last lecture, the rough picture of the history of the universe. So as I mentioned, you can roughly divide the history of the universe into three periods. The very early universe, which consists of the Planck era, where you should expect effects from string theory, quantum gravity, and following the Planck era, also in the early universe, very early universe, you have the inflation period, this rapid expansion of the universe. Okay, and then the second big period in the history of the universe is the so-called early universe, early but not very early, which extends for much longer, up to about 380,000 years after the Big Bang. Okay, and finally the late universe, which is everything after radiation decoupling, after the time when the cosmological background was a bit. So anything after 380,000 years since the Big Bang until now is the late universe. So this periodization is potentially important because each of these eras has different subject of physics attached to it. Okay? So let's take it backwards. If you are an astrophysicist, then you actually work on problems related to the late universe, this magenta era. Okay? These are problems from neutron stars, star evolution, galaxy evolution, galaxy astrophysics, and interstellar clouds, and things like that. Okay, quasars, all of the stuff that enters astrophysics is here. If you are an astroparticle cosmologist, a subject called astroparticle cosmology, then you work on the orange era, the early but not very early universe. That's where you have things like CP symmetry breaking, which is supposed to be responsible for the space symmetry between matter and antimatter in the universe. Problems of quantum plasma, which are relevant in certain creation of hadrons, hadronic physics in the other universe. How you explain the abundance of light elements, which start forming close to the recombination period, and many, many others. Okay? So that's astroparticle cosmology. Nuclear physics is somewhat relevant here. Some people pretend it's relevant to the physics of neutron stars, even though physics of neutron stars is really a problem in QCD, which is a much wider subject than nuclear physics itself. So nuclear models are not, the standard nuclear models are not really useful in understanding neutron stars, but you can use QCD and of course general relativity to understand neutron stars to some extent. So after the problems of exotic states of matter in QCD, which are very badly understood because we don't really understand fully the phase diagram stuff. Okay, so this era is for particle cosmology. Of course, you need to know a lot about standard model, about hadronic physics, about platonic physics. So it's basically, as the name says, it's the intersection between particle physics and cosmology. And now about the very early universe, most of this stuff doesn't matter because almost none of it was formed yet. At the very late period of inflation, you have to explain how the interconcept goes into some kind of minimal potential, hopefully. That's the story of preheating and reheating. There's some intersection with particle cosmology. But before that period, you essentially deal with one or a finite number of inflaton fields, which are real scalar fields, coupled to gravity. Okay? And that's pretty much the only problem that matters. And you have to study that coupled system, ideally in a quantum regime, if you know how to quantize it. In that energy regime, you can gravity is semi-classical or classical, which is what most people do, but you cannot treat the inflaton field as being classical. So you can rely on the background approximation called the quantitative theory on curved space. So this is the fundamental tool during the inflationary regime. You treat the gravitational field as classical, and this is the first approximation. Maybe you want to include some back reaction effect in terms of self-consistent, hopefully self-consistent procedure. But first approximation gravity is pretty still as classical because you are still quite far from the Planck scale, about 3 orders of magnitude below the Planck scale during inflation. Okay? 3 orders of magnitude in energy below the Planck scale. So it's a reasonable approximation. So that's a domain in which we are interested in quantum interior and curved spacetime with scalar fields. This is the fundamental level. And then before that, during the Planck era, of course, all hell breaks loose. The inflaton becomes one of the many fields, low energy fields, produced by some sort of fundamental theory of gravity and matter. The leading candidate, I think, is still string theory, despite all the attacks. There is a counter candidate in quantum gravity, which has some problems, much worse than amplified frame, very serious problems at the level of formulating the gravitation, let's see. So you need some kind of fundamental theory, and you certainly need a quantum theory of gravity in order to understand the Planck. And that's the most mysterious part of all that spectrum. Just to clarify the difference between the tools and the names of the physics subjects that are relevant to each field. So the rest of this talk will focus on the inflationary period, where the basic conceptual tools are relatively well understood. We know how to do rather well, not with the theoretical problems, but we know how to do rather well quantitative theory and curved spacetime. Okay, which is well, a blessing in a way, but it's also a curse because we don't expect to see spectacular effects coming from quantum gravity. Now, what is the basic idea of what I will focus on next? Pretty much any reasonable theory, fundamental theory of quantum gravity, predicts that at low energies, sufficiently low energies compared to the Planck scale, you should have a wealth of scalar fields. Not just one real scalar field, but many real scalar fields. In string theory, these are called modular fields. They come from Calin computations or flux computations or other computations, the string theory or M theory, which is the supposed non-perturbative completion string theory. Okay. So one of the fundamental signals that could indicate that in this string theory or something like the low energy limit of string theory, like supergravity or whatnot, is relevant to the Planck era, would be the fact that during inflation you have more than one real scalar field. So the real scalar field in inflation is called the inflaton. So you should have more than one inflaton. Any of these speculations about fundamental theory of gravity is correct. Speculation, string theory, supergravity, whatnot. Okay, so that's why if you want to test string theory, let's say, for cosmology, to say whether it might have a chance of being true or not, one of the first things you want to know is whether you have a single inflaton or more than one. But then if you have two inflatons or more, that could be a huge number of inflatons. For example, Calabi-Yau spent a very well-studied classic Calabi-Yau computations with Titus string theory on the quintic. Okay, that produces 101 complex moduli. So this means 202 real spectrum. Real and imaginary part, for example, of cosmology. This, in general, there will be a huge number of real spectrum. But if you have at least two, you should have a way to see whether you can realize reasonable inflationary scenarios in such models. And that itself is not hard. Also, you need to find ways to identify whether the signal that you inherit after radiation decoupling, here in the CMB era, or maybe the gravitational wave signals that we inherit throughout, are compatible with multi-field models of just one field model. And that is already a problem, which is not so easy. And the reason why it's not so easy is that a multi-field model of cosmology, a cosmological model is more than one photon, is much more complicated. Even already at a purely classical level, when you don't try to factor anything in that model, it's much more complicated than a multi-field model. And that's for many reasons. First, because the classical dynamics of the model is complicated. Second, because the topology of the space in which the scalar fields take values for such a model can be very complicated, already for the field model. And third, because the kind of solutions of the best calibration motion around which you would like to expand the mechanization of the scalar field, which are compatible with what we already know about cosmology from the Bucharest-Magurele background, are very constrained, and they are very hard to find. And to find them is a whole song and dance. And you hope to be clever about how you find them rather than to try brute force, because as I will explain soon, brute force doesn't have a chance. Good. So now if I can have the second. Hopefully it's clear why we are using multi-field model. We are using multi-field model essentially because I'm a person who worked out his life on mathematical foundations of string theory and supergravity. And I want to manage those theories and then cover to nature. That's my but. Okay, that's the title of the talk tells you what I'm after. Good. So let me summarize the main points. String theory and supergravity computations typically produce many moduli fields. I explain what a moduli field is. A moduli fields are scalar, real scalar fields, which live on the uncompactified part of space-time. Use the word computation. Hopefully everybody has a big idea of what it is. Okay. I will simplify language. I will take a moduli field to be just a real scalar field. They sometimes appear coupled together in complex scalar field and even pattern learning, depending on the type of computation theory you have. I will just take them to be real. First, in general, we decompose a more complicated scalar field into real pieces. Okay, such moduli fields will generally be dynamical in the very early universe, which therefore contains gravity and a finite number of scalar fields so during the inflation period. Okay. And as I mentioned, you can treat gravity during inflation as classical, so first problem. Okay. At energies sufficiently lower than the Planck string scale, you also have to be able to neglect string effects if your fundamental model comes from a string computation, not just Planck effects. But higher than the Hubble scale. The Hubble scale is the energy scale characteristic of the inflation, which, as I said, is 12 orders of magnitude or more above the highest energy scale dependable at the other scale. So these ideas lead one to consider multi-field cosmological models. If one neglects higher order corrections, which might arise from the fundamental theory, so higher order corrections are usually higher derivatives in the fields present, such a model has a canonical coupling to the scalar fields to gravity. So again, neglecting higher order. The target space of the scalar fields is generally a manifold band whose dimension equals the number of those scalar fields, the number of real moduli. That manifold band is called the target manifold. And the very important observation is that this manifold has no reason to be topologically trivial. As you will see, it's pretty much arbitrary. You have to take it connected because you don't want to talk about multiverse theological subject. Okay. But except for it being paracompact, in general it's not compact, it's very compact. It has no other constraint, connected and paracompact. And you should realize, if you know anything about differential topology, that, oh my God, there's lots of those, especially since I don't require even compactness. Lots and lots of those, but lots and lots of complicated topology. So it's very complicated from the first moment. Okay. The simplest case is when M has dimension 2. In general, it's a non-complex surface. If you are at least vaguely familiar with non-complex surfaces, you will know that the classification is much more complicated than that of complex surfaces. It's not just given by single numbers of genus, as in the complex case, but also by a triplet of topological spaces in the general case, not necessarily oriented case, which characterize the RS1 space of ends of those surfaces. One person who brought very important contributions to that, the topological classification of non-complex surfaces is Simeon Stoilov, who was the boss in 1960. So already in 2 dimensions, for 2 real scalar fields, topology can be absolutely crazy. For example, the most important of these components of the space of ends can be a Cantor space. That's great. Good. Another important point is that the kinetic term of the scalar fields, because I have canonical coupling, as I mentioned before, is described by a Riemannian metric G. So this calligraphic G will control the kinetic term, you will see in a moment, of the scalars. And that Riemannian metric G is defined on this target manifold M. And it will be called the target space manifold. So M together with G becomes a Riemannian manifold, in generally non-complex. The fact that you can have a metric on N imposes no topological conditions on N. Because I already said that I'm assuming that N is paracompact. So I want to control the level of compactness in some way. I want to have some local to global principle. And it's a well-known result that any paracompact manifold, oriented or not, that meets Riemannian. So you have no topological coming, supplementary topological coming from the existing. And in general, the scalar fields, and we know this from many examples of fundamental theories and also required even in one field cosmology, will interact through a non-trivial scalar potential, which is modeled by a function v defined on M with values in R. Now, for physical as well as technical reasons, it is natural to take this function v to be everywhere positive. You can take it to be everywhere semi-positive. In what follows, I take it to be everywhere strictly positive in order to avoid some technical issues which can be addressed, but we'll just make the discussion even more complex. Good. So that's the stage. Let's see how these models look like. So this is just some definitions to clarify what depends on what. First, I introduce the notion of an oriented scalar triplet. So first, I should mention in this presentation, I make a further topological assumption, namely that the target space of the multi-field model that I consider will be orientable, and I pick an orientation. This is not a big constraint because you can always consider the orientation part of any oriented manifold. You can reduce this. Okay. So an oriented scalar triplet is an ordered system consisting of a manifold M, a Riemannian metric G defined on M, and a scalar potential V, where M together with G is a connected, oriented, and borderless Riemannian manifold. Okay, and V is a smooth function valued in R. I will take it to be positive in a moment, which is called the scalar potential. I will limit further for the remainder of the talk to the case of cosmological models with only 2 inputs. It's again for simplicity. A lot of what I say can be extended to multi-field models, but part of it hasn't yet been extended. Okay. And there are 2 physics and mathematics motivated assumptions. The first one is that M together with G is a complete Riemannian manifold. That's physically motivated. It ensures conservation of energy at the classical level in this model. And the second is that V is simply bigger than 0. This avoids some technicalities, which I want to not just bigger or equal than 0, but simply bigger than 0 at every point on it. And if I give you a scalar triple about the dimension, not necessarily of dimension 2, that defines the model of gravity coupled to a number of scalar fields, real scalar fields, which is equal to the dimension of it. Okay? And I'm considering such a model defined on a space-time with topology R4. Take R4, which is standard differentiable structure. And I consider this model. So here, little pi is the map from R4 valued into this scalar manifold M. Okay? If you choose the local coordinates on M, you can represent that as an upole of real scalar fields where little n upole, where little n is a dimension of M. If M is a surface, so little n is equal to 2, that's a doublet of real scalar field. So these are the scalar fields that I will call intervals. Okay. I need a space-time metric, a physical metric for Einstein's equation on my space-time, because topology is going to be R4, because supposedly we live in a spatially flat universe and there's a cosmological time, so the topology of space-time is supposed to be R4. Better than R4. Okay, so that's little g, the metric on R4. And they enter this action function. Okay. Now in this action function, big M is the so-called reduced Planck mass. It's Planck mass measured in units where h bar equal to c equal to 1, c being the speed of light. Okay. This object is the trace with respect to little g. I will explain more what it means, of the pullback of calligraphic G through phi. Okay, so this pullback is a symmetric covariant to tensor defined on R4. On R4, I have the metric G. I can raise any of the indices of the symmetric to tensor through that G and take the trace of the resulting homomorphism on the tangent bundle of R4. The result doesn't depend on which index I raise, because the tensor proceeding design, one of the indices I raise is symmetric. So that's a standard notation in Riemannian geometry, this trace of the G. So that's a trace of that symmetric to tensor with respect to G of that symmetric to tensor on R4. So this component, if you write it on this piece, if you write it in indices with respect to, let's say, the Cartesian coordinate system on R4, it's just a standard kinetic term of a scalar model, of a nonlinear sigma model. Good. Here, the term multiplying the square of the Planck mass is this Einstein-Hilbert term. Everything is multiplied by the square root of the absolute value of the determinant of little g, so the standard prefactorial volume, Riemannian volume form, pseudo-Riemannian volume form of R4 together, considered together with G. And finally, you have the term which gives you the interaction between the scalar fields mediated by the scalar potential V. So here, phi was the map from R4 into M, V was the map from M into R, so V composed phi is the map from R4 into R. Right? I can integrate it against the volume form of R4. R4 is in out, which is the canonical orientation. So here the Einstein-Hilbert term, so somewhere here is hidden Einstein-Hilbert gravity. You have nonlinear sigma model, that's a kinetic term for the scalar fields which I mentioned. But you also have an interaction term between the scalar fields given by the potential phi. That's what I was mentioning. Now it will be convenient for later to define the scaled Planck mass, which is just a notation. It's defined the square root of 2 over 3 times the reduced Planck. Okay? Now, how do you go from this model to a classical model of cosmology? So, a model in which you don't try to quantize the scalar field phi. As I said, we always treat the metric little g, the Einstein-Hilbert metric, as classical. But before we even discuss quantization and so on, how do you construct a classical cosmological model without in the absence of what cosmology is called fluctuation. Well, that's obtained as follows. You take G to be a specially flat FLRW universe. As I mentioned last time, FLRW stands for Friedmann, Lemaitre, Robertson, Walker. Discover the solution of quantum equations. So it has this form. A is an everywhere positive function. T is the cosmological time, which you can view as the coordinate x naught. So you choose Cartesian coordinates on R4, which are x naught, x1, x2, x3. You denote x naught by t. That will be my cosmological time. Okay. And you also take little phi to depend only on t, only on the coordinate x naught. Okay, and if you make that ansatz, you have a proposition which tells you what happens to the equation of motion that you derive from this. So the way it goes, you first derive the equations from this, and then you make the ansatz into the equation of motion, and you see what you get. Okay, to state the proposition, I have to define something more. It's a Hubble parameter that I mentioned last time, which is the logarithmic derivative of A of t with respect to t, which was the cosmological time. And I also define the scaled Hubble function. The scaled Hubble function is a map from the tangent bundle of the scalar manifold into real positive numbers. When I say the tangent bundle, I mean the total space of tangent bundle, which is given by this expression. Here, pi is the bundle projection of Tm. And the norm denotes the norm of vectors in Tm, computed with respect to the metric calligraphic G, to the scalar field method. So that's a Hubble function. Notice that since I assume that B is strictly positive, this function is in fact smooth on Tm, because under the square root you never hit zero. You always take the square root of something that's strictly positive. So that's one of the technical specifications that comes from that subject. Okay, so with these notations, the proposition is that when if you take the Hubble function to be positive, then the equations of motion are equivalent to the cosmological equation, which is this equation written here, together with the so-called Hubble condition, which is this condition written here. So now let's look at them. What is the Hubble condition first? Well, what is the cosmological equation first? It's the equation written here, where nabla t is, by definition, the covariant derivative of this time-dependent vector, tangent vector phi dot of t, with respect to phi dot of t itself. So it's an abuse of notation that I denoted by nabla t rather than nabla phi dot. Okay. So phi dot of t is just a tangent the velocity vector of the curve phi of t at the moment t. So here, of course, phi depends on t, but I didn't specify the interval. I have to take t to belong to an interval which is not reduced to a point lying on the real axis. Right?
So this happens on this manifold M, and the covariant derivative is
the covariant derivative is with respect to this match.
Yeah.
So everything now is an equation for curves defined on some interval, and the interval is the interval of real numbers, okay? And values in the Riemannian manifold M, calligraphic G, together with the other. Okay? So if I give you any Riemannian manifold, I can consider this equation, okay? With this definition for the Hubble function. Here I take the Hubble function. The Hubble function is evaluated here on phi dot of t, which is a vector of Tm. Okay. You multiply this phi dot of t. The notation here means the gradient of v relative to the calligraphic metric calligraphic G, which is a vector field defined on M. And it's applied, it's evaluated as phi of t. So you can immediately see that this is a well-defined and in fact geometric. It's defined without reference to any coordinate system. Second order differential equation on M. The geometric second order ODE defined on M, which depends, of course, on V and on the choice of the scalar field metric G, the metric which specifies the kinetic term. That term of the input, the real scalar field. And the Hubble condition does what? So it determines the Hubble parameter as a function of a solution of the cosmological equation. So if I give you a curve in M, which does satisfy the cosmological equation, I call that a cosmological curve. It's denoted by phi of t here. Then all you have to do is to apply the scaled Hubble function on the vector phi dot of t, then you get back up to a factor of 1 over 3 and not the Hubble function h of t. Since the Hubble function is the logarithmic time derivative of a of t, that determines a of t up to a multiplication constant, up to a multiplication constant, which has to be positive. A of t is taken. A is a scale vector or cosmological conformal vector in the FLRW union. So that determines the geometry of space. So everything got reduced to this. Now what is this? Of course, since the Hubble condition just determines something in terms of something determined by the cosmological equation, in fact all you have to do is to understand what the cosmological equation does. So as I mentioned, the solution to the cosmological equation are called cosmological curves. Such an equation turns out to define an autonomous dissipative geometric dynamical system on here by a well-known procedure. Okay. That dynamical system is called the cosmological system of the scalar triple MGB, cosmological dynamical system. And through that well-known procedure, any cosmological curve, so any solution of the cosmological equation, defines a cosmological orbit, which is a flow curve of that dynamical system. Is denoted by calligraphic O of phi. Is defined on the same interval definition of phi, and is given by this expression. So that's an evolution curve of the cosmological dynamical system. And of course, the correspondence with the evolution curves of the cosmological dynamical system is cosmological curves. So this explains how you can use the geometric theory of dynamical systems in the study of such models. So of course, the phase space of the cosmological dynamical system is dependent model of them, so it's generally very far from being topological trivial. So you cannot use the dynamical system theory in Rn just like that. Maybe locally that you have to use instead if you do that. Instead, you have to use the geometric theory of dynamical systems, which is good because it's now serious math science. It's not just all these, it's a little bit more, and quite a bit more. So good. We are doing real math. Good. Now the notion of reduced observables and functional conditions, this is quite technical. I will jump over it because I want to stress other aspects. What I want to mention is, okay, so how do you study a little bit cosmological curves? What can you say in the most plain way about them? So one thing you can do is to decompose them into two scalar equations, to decompose the cosmological equation into scalar equations. Okay, since it's really, if you choose some coordinate system on this surface, I'm looking at 2D models now, M, the cosmological equation is really equivalent to a system locally. It's locally equivalent to a system of two second-order ordinates. So a smart way to describe the system is to use not a local coordinate system only, though you can also do that, but to use a moving frame. And the canonical moving frame of a curve in M is the René frame. Since M is oriented, I can make it even nicer by considering the positive René frame of the curve. It's defined by two vectors tangent to M at the point phi of t. So vectors will of course depend on t, both of which are of norm 1 with respect to the scalar field metric calligraphic G. The definition is given here. The first one is a unit tangent vector, unit with respect to the scalar field metric. And the second one is obtained by rotating the unit tangent vector by an angle of plus pi over 2, so pi over 2 in the counterclockwise direction. I know what counterclockwise means because M is oriented. And that operation is given by an endomorphism of the tangent bundle of M, which I call J. That endomorphism squares to -1 because if I do a rotation of angle pi, which is corresponds to acting by J squared, since J corresponds to acting by pi over 2, right? Rotation of angle pi, I just go from my original vector to minus this. So it's clear that J is a complex structure. Now, which complex structure is it? Okay, it turns out that it is exactly the complex structure which is determined by the conformal equivalence class of G relative to the given orientation of that. So the well-known correspondence on an oriented surface between conformal equivalence classes of Riemannian matrix on the surface and positive complex structures on the surface. The complex structures called positive with the orientation of the surface, which is induced by the complex structure, coincides with the given orientation of my oriented surface. So that's what I'm alluding to here. So J is exactly that complex structure, which is determined by the conformal equivalence class of G through its procedure. It turns out that the result, you have to argue for it, is not hard. And the next question is, what is it exactly? How do we identify J? How do we compute J in terms of G? And this formula tells you how. You consider the volume form of the scalar field metric G, which is a two-form defined on N. And J is the unique endomorphism of Pm, which obeys this equation. J of J u v is equal to omega u v for every tangent vector u v at the same point to the manifold M. It's clear that this equation suffices to describe the operator J, because it holds for every u and v. G is a Riemannian metric, hence a non-degenerate bilinear form. So if I know the scalar product with vector G between Ju and any vector v, which is what this program gives me, I can determine Ju for every vector u, since u was by determining the operator J. And in fact, this formula, you can write it down, for example, in order form, and you can extract an explicit expression for J, which will be a nonlinear function of the coefficients of the Riemannian metric G. It's an algebraic expression. It doesn't depend on the partial derivative of G with respect to formula. I leave this for your domain. Write in coordinates and solve for J. What J is. Okay. Good. Now, with this explanation, I can also consider an increase in proper length parameter for phi. So, of course, this sigma is the name of the parameter. This sigma is the norm of phi dot of t times dt. And then I can take the cosmological equation from here and project it along the vectors of the frame, along tangent vector, unit tangent vector, and unit normal vector. And you get two equations, two second-order ODEs, which I just write in this form because I want to define some of the standard cosmological observables that appear in the literature on topic cosmological. The first one is the second-order ODE for sigma, for this proper length parameter. Depends on t, of course. So it's this equation, where dt is a tangential derivative of scalar potential. Tangential means with respect to the unit tangent vector t, defined here. And Vn is the normal derivative of d. That means with respect to the vector n of t with it's defined. So Vn appears in the second equation that we obtain by this projection, which I wrote in this form. So you see that that equation is really a second order ODE or something. Okay, but I write it in this form because I want to give you the definition of the so-called signed turning rate or signed turn rate of the cosmological curve phi, which is given by omega. Okay, so these two equations, which are equivalent, when taken together, are equivalent to the cosmological equation for two-field models are called the adiabatic and propagated. Good. Now, using this omega that I have here, I can define some other parameters, so-called kinematic parameters of two-field models, and the definition is given here. The definition is not very important. You use the Hubble parameter and omega to take some time derivatives and some ratios, and get this. They have some funny names, so there is a reason for the names, doesn't matter what the reason is. So the first three are the so-called first three slow roll parameters, or Hubble slow roll parameters, because sometimes people talk about potential slow roll parameters. The next two are the so-called first and second term parameters, and the last two are the so-called first infrared parameter and the so-called conservative parameter. And in cosmology, for a moment that you will understand, for a reason that you will understand in a moment, it is important to consider the so-called slow roll and rapid turn conditions. So from now on, I will further simplify my units by taking the reduced Planck mass to be equal to 1, which means not only I set bar and C equal to 1, but I also take the last remaining fundamental constant, the Newton constant, to be such that the reduced Planck mass potential to be equal to 1. I can always do that. I can work in so-called natural units, which are the units in which this happens. This means that M naught, the scale Planck mass, is equal to square root of 2. And with this, we have these definitions. So the so-called slow roll conditions, maybe the first, second, and third slow roll conditions are these conditions. The first slow roll parameter is smaller than 1. Much smaller than 1 is the first slow roll condition. If you require that the second slow roll parameter is much less than 1, that's the second slow roll condition. If you require that the third slow roll parameter is much less than 1, then the third slow roll condition. These are conditions which constrain separately one of these first three slow roll parameters. But you can also combine such conditions, and it's interesting to consider the following two combinations. They need a second order slow roll regime, which is obtained when you combine the first slow roll condition with the second slow roll condition.
So what's the difference between the first and the third?
First and the third what?
Condition. The third order slow roll regime. What's the difference?
Here you have three conditions.
And upstairs?
And upstairs you have three separate conditions, disjoint. Here I said is defined by the joint condition. Joint means and.
And upstairs is what?
Upstairs is a definition of three independent conditions. I just explained that epsilon much smaller than 1 is called the first slow roll condition.
Ah.
This condition is called the second slow. Simply a name, the first one gives you the name for the conditions, and the third one gives you the name for applying jointly the first three conditions. I think it should be clear. Good. So that if you impose the first slow roll condition, the second slow roll condition, and third slow roll condition together at the same time, that defines the third order. When you use the word order, it means that you do something joint. Good. So finally, I have to define the rapid turn condition. That's the condition that this parameter, which was the first term parameter, is much larger than 1 in absolute value. That's the same as saying that the single is much smaller than 1 in absolute value. And the sustained rapid turn regime is defined by jointly imposing the rapid turn condition and this condition, which requires that the second term parameter is much smaller than 1 in absolute value. And there's a remark here which says that if the second slow roll condition is satisfied, then the rapid turn condition is equivalent with the conservative condition. Conservative condition being that the condition that the conservative parameter C that you have here is much more relevant. This is through modular de-Euclidean motion, only for if phi is a cosmological term, only phi satisfies the cosmological. Okay, finally I have to define the adapted frame. That's a non-orthogonal frame defined on the complement of the critical vertex of the scalar potential. So you consider the following closed subset, the set of critical points of V on M. It's a set of those points in M where the differential of V vanishes exactly. It's clearly a closed subset of calligraphic M. And you take its complement. So you look at the set of points M where the differential doesn't exactly equal 0. That's called the non-critical set of M. It's an open subset of M since it is the complement of a closed set. And because it's an open subset of M, it carries the induced submanifold structure. Any open subset of a manifold has a manifold structure. Okay, I will tacitly assume that this M naught is not empty, which happens if and only if, since M is connected, that happens if and only if V is not constant on M. If your potential doesn't happen to be the constant function, which is a very degenerate case, then M naught will be non-M. Okay. With this preparation, I can define the adapted frame of M naught. So it's a frame defined on M naught, which will depend on G and V. But by abuse of notation, it's also called the adapted frame of the scalar triple, initial scalar triple MTP, since M naught depends on M and V. So the adapted frame of the scalar triple is the oriented orthonormal frame of M naught, defined by the following two vectors, N and tau. So N is a normalized gradient of V, normalized with respect to the metric calligraphic G. You see why I have to restrict to M naught, because to define the normalized gradient, I need the norm of the gradient to be non-zero, and that happens if and only if I'm at a non-critical point of V. Otherwise, I will divide by 0, I will have 0 divided by 0, and I wouldn't know what I'm talking about. And tau is just, again, J applied on N, so I just rotate this N by angle plus by the rotate it up to 90 degrees. And I consider them in this order, the order important, since I'm telling you that this is an oriented frame, so I vector this in the correct order. The order is N tau. So that is natural frame. And this characteristic defines this natural frame, oriented orthonormal frame, on its non-critical law, which is an order from manifold of underlying scalar manifold of scalar triple. That's called the adapted frame. The adapted frame allows you to define two other interesting things. So now consider a curve phi in this calligraphic M, in this surface. Okay. That curve has a Frenet frame, a moving frame, so a normal tangent vector, a normalized tangent vector, and a normalized normal vector to the curve. And you can compare this Frenet frame to the adapted frame at every point of the curve, which happens to be non-critical for V, which happens to lie in M naught, because only at such a point you have an adapted frame. Okay. If you do that, okay, you can do that. You can compare these frames much deeper by rotation in 2 dimensions, because they are at every point. They give you two oriented bases of the tangent space to M at that point, which is just R2, right? And that tangent space carries an orientation because M is oriented. So they must differ by an orientation in that, by a rotation compared to that orientation, some angle which lies between 0 and 2 pi. But I can shift by 2 pi the interval definition of the angle, so I can take the principal determination of the angle to lie in the interval minus pi pi, semi-open interval. And that's the formula that relates T and then as I explained. Okay? So this is called the characteristic angle of the curve phi. Okay? It depends on the data of the scalar triple, on the method G, and on the potential V, and on the curve phi. And it works for every curve, not necessarily a solution of the cosmological. And once I compute the characteristic angle of a curve, I can consider its sine, the sine of its sinus, but with this principal determination chosen here, it's the same as the sine of theta itself. And I call that the characteristic sine of the curve phi at the moment t. Everything is computed ideally in it's computed at given time, cosmological time. So with this definition, you have a proposition which relates some of the parameters that I defined before. It relates this parameter eta parallel, which is the second slow roll parameter, and eta perp, which is the second term parameter, to the characteristic angle, and to this parameter, which was called the conservative parameter. So these are the formulas. You can prove that. So now let me tell you something about consistency conditions. And you see that this very high concept. You will jump over a lot of technical details to follow, but I want to give you what we get about, what's the mileage we get. To state what those are, I introduce a notation. So for any vector fields xy defined on this surface M, on the scalar manifold, we use this notation for the Hessian of the potential V applied to the vector field x and y. So Vxy is the Hessian of V applied to x and y. The Hessian of V is the Riemannian Hessian of V, so it depends on the scalar field metric telegraph G. It's defined as the covariant derivative of the exterior differential of V. Because G is a Riemannian metric, the distortion free, you can easily prove that the Hessian, Riemannian Hessian is a symmetric covariant to tensor. Okay. Defined one and good. Then there's a proposition that you can prove. This is a computation, rather ugly computation, but not that difficult, which tells you that the VTT, so the Hessian of V applied to this moving tangent vector T to a cosmological curve, and BTN, again, T and then the vector of the Frenet frame of a cosmological curve, so curve which is a solution of the cosmological equation, satisfies this relation. So this relation relates BTT and BTN to the Hubble parameter and to these parameters that I showed. So those parameters are among the so-called standard cosmological observable to cosmology. And using this proposition and a sequence of arguments and computations, which is not entirely trivial, you can prove the following theorem. So suppose that the third order slow roll conditions, again, the third order means all of these conditions are satisfied simultaneously. So the first slow roll condition, the second slow roll condition, and the third slow roll condition are satisfied. So suppose that that's true. And also suppose that the small rate of term condition, that's the condition that that's including of mu is much smaller than 1, which I mentioned before, is satisfied. So with all these assumptions, you can show that the cosmological approximates like this in terms of the conservative parameter and this characteristic sign S that I introduced before. And furthermore, these equations, together with some other equations, imply these equations. So these are approximate equations, right? When I'm using some much smaller than 1 conditions, I can only get some approximate. So this is a system of approximate equations. Moreover, this system of equation admit a solution, little c. I view them as equations for C, fixing everything up. I need a solution little c, so that was a conservative parameter which is much smaller than 1, if and only if the following conditions. So these equations tell you that little c is determined by the other parameter. And I want to be in this sustained rapid turn regime. And by this proposition, that regime requires in particular that c be much smaller than 1. In order to ensure that, I want that these equations admit a solution C, at least one solution C, is much smaller than 1. And the theorem tells you this happens if and only if this algebraic condition is satisfied. Here you have the elements of the Hessian of V on the adapted frame components of it. Okay, so it's little n, little tau. Here there's a hidden assumption, namely that I'm considering a cosmological curve which is non-critical, which means that it doesn't intersect the critical locus of this, so that its image is contained in the non-critical locus, so that n and tau are represented. So, and this of course these conditions must hold at every point of such a non-critical. It's an approximate condition which relates where algebraically the Hessian components of V in the other system. Now notice that this condition knows nothing about cosmological curve. It's just a condition which constrains the parameters of the model. The parameters of the model are the scalar potential and the scalar field band, calligraphy. N and tau were defined in terms of these parameters. Therefore, the Hessian components depend only on this parameter. This is a condition which constrains the model itself. It constrains the scalar triple without making any reference to the kind of curve. So this theorem has the following important corollary. A cosmological curve, so solution of the cosmological equation of your model, satisfies the sustained rapid term conditions. I put them here with third order slow roll, which means it involves the third order slow roll conditions as well as the sustained rapid term conditions at the cosmological time t, if and only if the following condition is satisfied at the point of the non-critical, the point of the non-critical manifold Bernard given by phi of t. Mainly these algebraic conditions. If I require exact equality here rather than approximate equality, I get something that's called the SRT equation, which is now a non-linear PDE for the parameters of the model. So the SRT equation is the following condition which constrains the target spin matrix G and scalar potential V on the non-critical submanifold Bernard. It's this equation with exact equality, but with approximate. A metric on M naught, a scalar field metric, which satisfies the equation for a fixed scalar potential V, is called an SRT metric relative. So this SRT equation can be written as a nonlinear differential equation for the pair GB on M naught, nonlinear geometric differential equation. So some of you may have heard, all of you, that there's a notion of geometric PDEs, okay, which are defined within jet bar powers. And that's what I alluded to. I won't go into it. When you fix a scalar field matrix, then this can be viewed as a nonlinear second order PDE for V, geometric nonlinear second order PDE for the scalar potential. But when you fix the scalar potential, which is what I will do next, it can be viewed as a nonlinear first order PDE for the scalar field matrix. That's very interesting. It means that that regime, the third order slow roll with rapid time regime, which is very important in cosmology, can only be attained if the parameters of your model are very close to parameters which satisfy the SRT equation. In other words, the vast majority of intuitive cosmological models cannot realize SRT equation. SRT equation requires the existence of SRT curves. SRT curves are solutions of the cosmological equation which satisfies third order slow roll together with the second order sustained rapid transformation. So why is that important? Because there are only two regimes that until now have been shown to be compatible with cosmological observations from the CMB. If you assume that you have a two-field model, what we already know about the CMB from current data requires you to have a solution of that model that would produce this data in our current universe that is either a slow roll, slow current solution, which is defined by some of these inequalities by different mathematics, or a slow roll rapid current. If the solution, if you want that to be a slow roll rapid current solution, an SRT solution, then that is only possible if your model approximately satisfies that approximate function. So the vast majority of models cannot do that, therefore they are ruled out by current experiment. A similar argument works for SRT. for SRST, for the slow roll, slow turn curves. Nobody can read on paper on that. I have one interpretation, but similar methods. So in other words, combining this result and the result of the interpretation, the vast majority of cosmological models are already, two-field cosmological models are already ruled out by Calin. A model with good models will cluster around models, statistically cluster, probability theory or statistics if you want, around models with satisfying this equation itself. They have to be close enough to it. So pause for a moment to realize what they are saying. What are we saying? Combining everything that we did before. Well, I mean, for 50 years now, we had a lot of smart banks scientists who are telling us string theory is untestable. You have all this huge number of Gaussian string complications, background, whatever, what are true. It's untestable. Well, I can tell you that they can be ruled out. If you have a complexification string theory which leads to, let's say, a single complex modulus of two real scalar moduli, that complexification is ruled out by current observation data unless the parameters you get from computation string theory satisfy this one or are very close to it. Wait. So those people were talking nonsense all this time. It can actually be tested. Even with current data, we can put constraints. What about the next 50 years? Okay, this is a two-field model, so it's a toy model, but the logic that leads to this can be applied to multi-field model. So voila, here is one way to devise effective tests of quantum gravity today. Now, of course, from here to what you need, of course, to expand a lot of this theory and combine it with partial computation and so on.
Well, I didn't catch. So, those data that you are talking about, that are available from the measurement, so they support one of those regimes that you...
Yes, SRT or SRST.
So that
not only
optimal
they
development of the
they
universe...
rule out any other regime. If you have a two-field model, unless you have SRT or SRST trajectories, that model violates current data. Therefore, any model you are interested in must allow for SRT or SRST trajectories. I'm telling you that a model allows SRRT trajectories if and only if it satisfies that person first. And there's a similar result, which I don't discuss here. It's in preparation, which says that the model satisfies SRST if and only if it satisfies a different constraint, but it's of a similar nature. It's an approximate nonlinear geometric field. Therefore, vast majority of models are better. Therefore, all string complications which need to models which fail to satisfy this condition, at least approximately, are better. Ruled out by current data. So yeah, it's then testable. Sure, these are two-field models. You need to do it for n-field models. You will get much more complicated equations. The test has to be done numerically. Neural networks, pattern recognition, advanced AI methods, whatnot, for the future. It won't be done like this. But the concept is important, the principle. So yes, it is possible to test. That's effective falsifiability. The strongest sense of falsifiability in Popper's book, for those who have actually read Popper. It is falsifiable. Good, that's my point. Okay, you can play some games, you can fix the conformal class of G to simplify things. Fixing the conformal class of G is equivalent to fixing the complex structure J. You do that, the result is, lo and behold, a compact Hamilton-Jacobi equation. So, Kastia has been telling you how interesting and beautiful this compact Hamilton-Jacobi geometry is. And compact Hamilton-Jacobi is here. And there's a beautiful mathematical theory behind, which is still it's in fast development, by the way. It's a very subject of growing interest in mathematics. Okay. You find that this tesseract equation takes this form, where F plays the role of a contact Hamiltonian. The underlying contact manifold is the first jet bundle of a bundle of half lines, which I call L plus. This bundle of half lines is a bundle of positive determinant half lines of your manifold. So what's the bundle of positive determinant half lines? Well, so the bundle of determinant lines is a real line bundle whose which has the volume form as a global. Okay, that's because my manifold. That is, if it were not oriented, it would be not a real line bundle. Okay, that's simply defined as the determinant bundle of T star n. So it's the second wedge power of the cotangent bundle of M. In this case, it happens to be trivial because M is oriented. Okay? Because M is orientable, in fact oriented, I chose an orientation. Inside each of these determinant lines, I have a positive determinant half line determined by orientation. Right? Because an orientation of M means it's the same thing as a coherently chosen orientation of the tangent spaces of M. And the determinant line of an oriented vector space comes with a positive half line. So that's why. So I have a natural bundle of positive half lines, state to M, which is denoted by L plus. Okay? It's a fiber bundle whose fibers are isomorphic to the positive real axis. Right? Its total space is three-dimensional because it's a bundle defined on a two-manifold on its surface. I take the first bundle of that. Okay, so I add two formal momenta. It means to take J1. So I get some five-dimensional manifold, the total space of the first bundle of that. That five manifold carries a natural because the first jet bundle, the jet bundle, there is a natural convex structure, which is Casting explains for the Cartan convex. So J1 of L plus is naturally a contact manifold, a five-dimensional contact manifold, the non-trivial topology in general, because even though L plus is topologically trivial, the base manifold is a surface, and as I said, it is in general non-complex surface, a non-complex oriented surface in space, and those can be solely created. So it's an interesting topology. Okay, but the non-triviality of the topology comes only from the base. Okay? There's a notion of local isothermal coordinates on M, which are determined local complex coordinates relative to the complex structure J, determined by conformal equivalence class of G. And this coordinates depend on G, on the scalar field metric. Okay, they are defined as the real and imaginary parts of a complex coordinate relative to J. In such coordinates, that's why they are called isothermal for historical reasons. The scalar field metric and this volume form have this very simple form. So it tells you that locally the scalar field metric is conformal to the Euclidean metric written in isothermal coordinates. Anyone can write explicitly this contact Hamilton-Jacobi equation as a nonlinear first order PDE for the conformal exponent Roman phi. So here I denoted the conformal vector by e to the power 2 Roman phi. Roman phi has nothing to do with Greek phi, which was curve. So it can be written explicit. And of course, you get something complicated, but it can be done. Okay? It's easy to show that the change of localized thermal coordinates corresponds to a contact vector. Okay. So I will not explain all of this. These are some notations that you have to introduce to write this contact Hamiltonian explicitly. I jump over that. Here is the contact Hamiltonian written with those notations. It's an ugly length expression if you substitute the definitions here. It doesn't really matter. Here there's a Laplacian with respect to this locally defined Euclidean metric, dx1 squared plus dx squared. Okay, U is the contact coordinate. The coordinate along the fiber is L plus. P are the formal momenta. P1 and P2. X1 and X2 are the momentum. So you have two coordinates, a contact coordinate Q and two momenta associated coordinates, and this is the A is defined here, it's linear in the PI. B is defined here, it's again linear in the PI. Epsilon and J is a Levi-Civita symbol, not length, but a symbol. I don't have any spirit of the engine. Good. And the contact Hamilton-Jacobi equation locally, in this localized thermal coordinates, takes the standard contact Hamilton-Jacobi. The first order, highly nonlinear, PDE, for a function Roman phi, which depends on x1 and x2. It's non-autonomous in the sense that it also depends explicitly on phi, not just on its derivatives, and its coefficients will depend on x1 and x2. And you can write it very explicitly and you can identify the coefficients and so on. The important thing from this formula, from this computation, is that this contact Hamilton-Jacobi equation is proper in the sense of Crandall and Lyons, which means that the contact Hamiltonian is non-decreasing as a function of u. Because this term here is semicolon, or everywhere on the non-critical harmonic problem 1. This means that the Dirichlet problem can be approached globally using the theory of viscosity solution. Now, of course, some people at least should know that there's a well-developed theory of viscosity solutions that comes from the early 1980s, initiated by Crandall and Lyons, which has the major subject in theory of nonlinear PDEs. It applies to PDEs of first order and second order, obeying a certain regulated condition. This is the first order case. The regulated condition here is what I'm stating. This is regular in the sense you can apply that theory. What's the purpose of this theory? The point is that, of course, locally you can always study any PDE using a method of characteristics. But the method of characteristics has a huge drawback, which is very manifest in a nonlinear case. Namely, two characteristics can intersect. At that point, the method of characteristics breaks down. That's exactly what happens here. The problem of constant or intersecting characteristics is crucial here. So you can only obtain local solutions. So the problem is, can you extend such a local solution to a global solution of a Dirichlet problem? The answer is, in general, no. The classical solutions, since the questions here, because of my assumptions, are C infinity in them, okay, the classical solution will be very rare, will be at least a class CP. Okay, but then it breaks down somewhere. It fails to be a class CP. It then goes to infinity, or it fails to be, it becomes discontinuous, or its partial derivative is fair to make. It fails to be different. So what do you do there? Do you have existence and unicity theorems for the, let's say, the standard boundary value problems, the Dirichlet mix, etc., for such equations? Yes or no? And if you have them, in what sense do you have to consider it? You cannot consider classical solution. Clearly, those don't count. So you have to consider some kind of general solution. The kind of general solution that works in the regular case for first and second order PDE are the so-called viscosity solutions of Crandall and Lyons, which are defined by certain inequalities. Those inequalities are described by a series of top-point functions and overcome. I won't go into details. It's a standard subject in the theory of nonlinear. One of the most powerful methods that applies in particular to mechanics, to the study of solutions of the ordinary Hamilton-Jacobi equation. So it's not surprising that it will appear here. This is just a complex version.
I will be talking today.
Good, very good. So you are in business. It's actually a very nice equation. It looks ugly, but it's very nice from a conceptual point of view. You can apply standardized here. Okay, and then you can say quite a bit more. Here I show you how viscosity solutions converge to how some viscosity deformations, the technique of viscosity deformations, converge to a viscosity solution in some very specific cases. You can study the quasi-linearization as this theory goes to a critical point of the potential, scalar potential of this equation. Why is that important? Because in most cosmological scenarios, these two fields of the model are supposed to settle close to a critical point of the potential. So if you have an ideal critical point, in fact, a non-general critical point, it's interesting to study, to approximate this complicated nonlinear TP close to the how. Ignore the details. I'll just tell you, just to give you some idea what results we have. You can study solutions which blow up at a critical point. You can further even study a linear approximation for solutions which blow up at a critical point, and that PTE. You can derive many other results. You can find them in our preprint. You can graph the viscosity approximations of these viscosity solutions in close to critical points. You can graph characteristics, and here you can see how characteristics intersect. There's a problem intersecting characteristics with dimension. So yeah, locally with the solutions. We did that as well, but globally not. Okay, this is again a plot of characteristics and the solution. So you see how explicit we get. We did this with Mathematica. We didn't use specialized code. We much faster, much powerful. You can already get this sort of very explicit numerical results and so on to build these fiducial models. Fiducial models are two-field models which satisfy this SRT equation, this constraint for the particles on the nodes with strict equality. They are those models around which cosmologically good models must cluster. They are the idealized model. There will be some curves in the space of all models, some regions in the space of all models which consist of a fiducial model. So if you identify fiducial models for SRT integration, you know where to look. Any model that doesn't, it's very close, that doesn't cluster close to a fiducial, to the region of fiducial models, it's ruled out. So fiducial models are what you should look at. The question is, how do fiducial models look like? Well, for this, you have to solve the SRT integration. How we solve it? We fix the conformal, we fix the scalar potential, fix the conformal class of G, solve this boundary value problem or an expert problem with some technical detail for the resulting contact and methodology of the equation, and we using the theory of respective solutions. So very explicit recipe for how to build fiducial model. And here we are giving you some examples of how fiducial model looks like. Is not testable? Well, of course, you want to do it for a model like 202 here. Yeah, sure. You need to have some very serious code and many other things, but it can be done. Okay. So hopefully I convinced you that it is done. When gravity is not untestable. But we have to have a few ideas, different from what the crowd shouts at us. First, you have to realize that, yeah, indeed, you accelerate that we don't have much chance to reach those energies. But where do we reach those energies in, for example, in cosmic radiation? Something like 10 to the 19 GeV, we observe in cosmic radiation. So at the moment, we have much higher energies available from cosmic observation. We already know a lot about cosmology. We can see through all this late universe noise using the SEENET-MTP. We'll be able to see much further through this noise using gravitational waves. In the future, we'll probably also be able to see through it using neutrinos. A lot of stuff is coming down in terms of data. So we can see through energies, at least 3 orders of magnitude below the Planck scale, through looking at this inflationary region. In the future, we'll probably be able to see even closer to the Planck scale. We'll have a lot of data. And here are some first ideas of how we can use them to rule out free potential or supergravity. or any sort of data theory that produces more than one input, as this here is fundamental theory statement. That's my point.